Hey guys, it's Miss Johnson and I'm here to bring you our notes video for Unit 7 Notes 5. Today we are talking about how to identify and solve independent and dependent events. Probability of independent and dependent events. So if we take a look up at the top, just a review kind of from yesterday, if we look at the probabilities of the following, a fair number cube is rolled, find the probability of each. For A, we're looking for the probability of getting a 2. Well, there's only one 2 on a number cube, so the number of successes would be a 1, and there's 6 total outcomes, so that'd be a 1 out of 6. We could make that a decimal, or we could just leave it as it is, and that would be fine. There's no way to reduce 1/6, so that's your final fraction there. The probability of something being even, if I think about a number cube, the even numbers on a number cube are 2, 4, and 6. There's 3 of them, so that's 3 successes out of 6 total. Oh, and I almost circled it, but 3 6 can be reduced into 1/2, and that is my final answer there. And then the probability of something being prime. So let's just review prime numbers. Prime numbers are numbers with only 2 factors, 1 and itself. So if I think about the numbers on a number cube, 1, 2, 3, 4, 5, and 6, 1 is one that people often confuse. 1 is one that people think is prime, but 1 actually only has 1 factor. So it doesn't have 2 factors. 2 has 2 factors, so this one is 1. 3 has 2 factors. 4 has 3 factors because it can be divisible by 1, 2, and 4, so it has 3 factors, so that one's out. 5 has only 2 factors, 5 and 1. 6 has actually 4, 1, 2, 3, and 6, so that one's out because that's a composite number. So I have 1, 2, 3 successes out of 6 total outcomes, which again is 1/2 if I reduce that. So remember that probability is a number between 0 and 1. It has no label, so it's just the fraction or the decimal that itself that we have written. Let's take a look at the next set of examples. Now we're looking at a number cube that's rolled twice. If we want the probability of getting 2 4s, we need to set up 2 probability fractions. Okay, 2 probability fractions, because I want 2 different things. This is 2 different events. This is like event 1 and event 2. So I have 2 different fractions there. So then I think about what's the probability of each one? Well, we want a 4 for this one. That's a 1 out of 6 because there's only one 4 on a number cube. And we want a 4 for this one for event 2. That's another 1 out of 6. So I have 2 probabilities of 1 out of 6. I take those and I multiply them together. I want both of these things to occur at the same time. I want both of these things to occur at the same time. So if I want them both to occur at the same time, that means I need to multiply them together. 1 times 1, when we multiply fractions, goes straight across the top, straight across the bottom. 1 times 1 is 1. 6 times 6 is 36. And that is my probability there. If I look at the next one, I want the probability of a 2 and then a 3. So what's my success of getting a 2? And then what's my success of getting a 3? Those are 2 separate events that I want to happen at the same time. Well, my success of getting a 2 is 1 out of 6. My success of getting a 3 is also 1 out of 6. Again, I'm multiplying them together because I want them both to occur. So then I multiply. 1 times 1 is 1. 6 times 6 is 36. No way to reduce that. That again is my probability. If I look at the next one, probability of 1 and then any number, my probability of 1 would just be 1 out of 6, but my probability of any number is actually 6 out of 6. I'd be happy with any number that I get. So I multiply those together. 1 times 6 is 6, and 6 times 6 is 36, but 6 out of 36 is 1/6. That also should be clear to you because 6 over 6 is actually just 1. So if I take 1/6 times itself, I get 1/6. But either way you look at it, you end up with 1/6 for a probability there. So these are all what we call dependent events. Okay, these were all, I'm sorry, independent events. These were independent events because these were 2 events that we were wanting to happen at the same time, but one didn't affect the other. Okay, so now let's just define those three terms. Let's review what probability is, and we talked about this yesterday. Probability is the number of successful outcomes talked about, or divided by the number of total possible outcomes. So the probability of rolling a 4 is 1 success out of 6 possibilities, or 1/6. Okay, but now we have two different types of events when we want things to occur at the same time. So independent events is when the result of one event has no impact on the result of another event. No impact. Okay, the result has no impact on the other one. And then I'm sure you can think of what dependent will be. Now the result does impact the other. Okay, the result does impact the other. So this one impacts the second. Okay. If we look at examples for both of those, if I look at independent events, rolling a die and then drawing a card from a standard deck of cards, those two things have nothing to do with each other. When I roll a die, it doesn't impact the standard deck. When I draw a card, it doesn't impact the die. So these are independent of each other. But if I look at the second one, draw an ace and then a 4 from a standard deck without replacement. That's the key phrase there. Without replacement, meaning when I draw the ace, I don't put it back. And then I go back and draw a 4. Well, at first there were 52 cards to draw from. Then when I got down to the 4, now there's only 51 to draw from. So that made an impact on the second event. Okay. Now, one thing that I want you to take note of is that these are all probabilities that we multiply. And the reason that we multiply these probabilities is because we want them to occur at the same time. We want them both to occur. Sorry, my handwriting is not well today. Want them both to occur. Or I should say all, because there may be more than two. We want them all to occur. Okay, so we're going to be multiplying probabilities today. So let's just practice identifying what's independent and dependent. If I look at number one says choosing the color and size of a pair of shoes. So choosing the color and size of a pair of shoes. Now, theoretically, when a shoe company makes a bunch of different styles of shoes, they're going to make each style in every size that's possibly available. So choosing a color and a shoe size, it's not like when you pick a size 7, the purple shoes go away. Okay, these are independent events. Okay, these are independent events. Because again, theoretically, the shoe company makes every color in every size. It's not like one has to do with the other. If we look at number 2, choosing the winner and runner-up at the dog show. Well, theoretically, you choose the winner first, and then once you choose the winner, the runner-up is out of a lesser number of dogs. So these would be dependent events. Because once you choose that winner, there's one less dog to choose from for the runner-up. Number 3, choosing a president, vice president, secretary, treasurer for student council, assuming that each person can only hold one position. Same thing. Theoretically, you pick your president, and then once you pick your president, there's one less person in the student council to pick the vice president, and the one person can't do both jobs. So the number of people that are available are less by 1. Then when you go to pick your secretary, the number of people that are available are less by 2. Okay, so when you picked the president, that affected the vice president. Then when you picked the vice president, that affected the secretary, and so on and so forth. These, again, are dependent probabilities because one affected the other. And then the last one, selecting a fiction book and a nonfiction book at the library. So when you go into the library, you've got your fiction books and nonfiction books, and they're usually separated. And when you pick a book, it can't be fiction and nonfiction at the same time. So when I pick a book out of the fiction section, I haven't touched the nonfiction section. When I pick a book out of the nonfiction section, I haven't touched the fiction section. So these two things are independent of each other. Independent. Okay. So now let's practice actually calculating some of these probabilities where we want a couple things to happen at the same time. In number 5, it says at a picnic, Julio reaches into an ice-filled cooler containing 8 regular soft drinks and 5 diet soft drinks. He removes a can, then he decides he's not really thirsty and puts it back. What's the probability that Julio and the next person reach into a cooler, both randomly select a regular soft drink? Okay, so we've read through the question. Now let's figure out what we're trying to find. What is the probability that Julio and the next person reach into the cooler and choose a regular soft drink? So we're going to have a probability for Julio. We're also going to have a probability for the next person. Okay. We're also assuming that Julio is going to get a regular soft drink, and the next person is also going to get a regular soft drink. Okay. So now let's look at these probabilities. Okay, that's the first thing that I do. I always figure out what I'm trying to find first. Before I try to set up probabilities and set up fractions and all that stuff, I always figure out what I'm trying to find. So now I can clearly see that I have 2 events going on. I have an event for Julio and I have an event for the next person. Now I'm going to go back and think about what these events actually look like. So I know that there are 8 regular and 15 diet, or I'm sorry, and 5 diet. When I put those two together, there are 13 total soft drinks. Okay, so there's 13 drinks in the cooler. So now I need to figure out what my successes are. Well, the regular soft drinks, there's 8. So for Julio, a success looks like 8 out of 13. Now, the next person, whoever comes up behind Julio, is also looking for regulars, so that success is also going to be 8 out of 13. Now, the reason I knew that this next person was going to be 8 out of 13 is because of this right here. I want you to underline that for sure in your notes. Julio puts the soft drink back. So since he puts the soft drink back, there are still 13 soft drinks in the cooler. Okay, the number didn't change. Now, since Julio didn't actually affect the number that were in the cooler, these are independent events. And now we actually calculate them. So we want both of these things to happen. We're going to multiply them together, and I end up with 8 times 8 being 64, and 13 times 13 being 169. Now there is no way to reduce 64 out of 169, but it's probably more applicable to find the decimal in this case. Once you get into numbers that are pretty big, it doesn't make sense to really look at it this way, so we usually calculate the decimal. I always like to round to the 3rd decimal place, and in that case it would be 0.379. And when we're rounding to the 3rd decimal place, this is the decimal that I got on my calculator, 0.3786982. So if I want to round to the 3rd decimal place, I want to round to that one, I need to look at the 6. And the 6 tells me to put the 8 up 1, so I go up to 9. Remember, that's where I turn into an approximately equal to. So this is my probability. It's approximately 0.379. Let's take a look at number 6. In number 6, it says 3 cards are drawn at random from a standard deck of cards without replacement. Find the probability of drawing a heart, another heart, and a spade in that order. Okay, without replacement. So again, I like to start with what am I finding? I want to get a heart, then another heart, then a spade. So I want heart, heart, spade. Okay, so now I can go back and look at what's happening with my standard deck of cards. So I know that I'm not putting them back. That's what without replacement means. So if you need to write that down, not put back. So I'm going to take the cards out and I'm going to keep them. I'm going to hold them. I'm not putting them back into the standard deck. Keep in mind the standard deck of cards, the makeup of a standard deck of cards that we talked about yesterday. We put that picture in your notes and you also listed some details in a little table. So let's just talk about how many hearts there are and how many spades there are. Well, there's 13 of every suit. So my first probability is going to be 13 out of 52. Now my second probability, I'm taking one heart out right here. When I take one heart out, now I have one less for the second probability. So now I only have 12 hearts and I only have 51 cards because I took out a card and I took out a heart. Then for this spade, I still have 13 spades because when I've taken out 2 hearts, I haven't touched the spades at all. So I still have 13 spades, but I've taken out 2 cards overall. So the total number of cards that are left for that probability are 50. Okay, so the fact that these denominators change, the total number of outcomes changed, tells me that these are dependent events. One event had an impact on the other because it changed the bottom. Again, this impact had an effect on that one because it changed the bottom. And you can also tell that from without replacement. If we're not putting them back, then we're changing the total number of cards in the deck. So that's a dependent probability. Now we want all of these things to happen, so we're going to multiply these together. So when I do that, 13 times 12 times 13 is 2028. On the bottom, 52 times 51 times 50, big number here, 132,600. See, this is where it's really more applicable to find the decimal rather than try to take your time to reduce the fraction. So I'm just going to straight type this into my calculator. And what I get is 2028 divided by 132,600. I get 0.152941 dot dot dot, and it goes on and on and on. So again, I want to round to this third decimal place, so that tells me I need to look at that one. And the 9 tells me to push that up. Oh, I'm sorry. Oh my. I am looking at this wrong. This is a 0 in front of the 1 behind the decimal place. Let's try that again. 0.15294. There we go. I missed that first 0 there, so check that. If I look at the third decimal place, it's this 5 right here, and the 2 actually tells me to keep the 5 the same. So my probability here is 0.015. That's how I round that off there. Sorry, I missed that decimal. Goodness. Okay, so let's move on. Take a look at number 7. In number 7, there are 3 miniature chocolate bars and 5 peanut butter cups in a candy dish. Liz chooses 2 of them at random to eat. What's the probability that she chooses 2 miniature chocolate bars? Okay, so look at what you're asked to find. What is the probability that she chooses 2 miniature chocolate bars? Okay, so if she's choosing 2 miniature chocolate bars, we want a miniature chocolate bar and another miniature chocolate bar. Okay, that's 2 events. Then the next thing we have to figure out is what is the probability of each of those events? Well, there's 3 miniature chocolate bars and 5 peanut butter cups. So that's 8 total. 3 miniature chocolate bars would be my success, so I have 3 out of 8 the first time. Now, we assume that when she takes this miniature chocolate bar out of the candy dish, she's not putting it back. She's going to eat that candy. So that means our number of candies goes down to 7, and our number of miniature chocolate bars, because she's taking 1 out, is going to go down to 2. So these are dependent events. The first event impacted the second event. And now I want both of them to occur at the same time. When I multiply, I end up with 6 out of 56, which is approximately 0.107. Again, look at that fourth decimal place to round it up or stay the same on the third decimal place. Number 8, in a state lottery game, each of the 3 cages contains 10 number balls. The balls are each labeled with one of the digits from 0 to 9. What's the probability that the first 2 will be even, and that the third will be prime? So 3 that we're picking out here, we want an even, and a prime. Okay? Now, when I go back and look at the successes and totals for each of these, there's 3 different cages. So when I take 1 out of the first cage, I haven't touched the second cage at all. So these events are actually going to be independent of each other because one does not affect the other because they're 3 separate cages. Now, if I look at each one individually, even, you have to assume that 2, 4, 6, and 8 are my even options. 0 is neither even nor odd, so I would treat that as neither. But if I look at 2, 4, 6, or 8, that's 4 options out of 10 total. And then again, like we said, this cage doesn't affect that cage because they're separate and they each have all 10 numbers in them. So an even again would be 4 out of 10 because 2, 4, 6, and 8, there's 4 even numbers. Then if I look at prime, remember those prime numbers are numbers with only 2 factors. So we talked about 0 is nothing. 0 doesn't have any factors. 1 only has 1 factor. So 2 had 2 and 1. 3 had 3 and 1. 4 was composite. It had an extra one. 5 had 5 and 1. 6 was composite. It has 1, 2, 3, and 6. 7 is only 7 and 1. 8 has 1, 2, and 4 and 8. 9 has 1, 3, and 9. So it's just these 4. So 4 out of 10 for prime also. So now when I multiply those together, 4 times 4 is 16, and 16 times 4 is 64. And then 10 times 10 times 10 gives me 1,000. So 64 out of 1,000, this is going to be equal to 0.064. And this is an equal sign because no rounding. Okay, just a couple more questions to look at. Number 9, find the probability of drawing 3 cards of the same suit without replacement. So there's that without replacement again, meaning I'm not putting them back, meaning they're going to be dependent. So I want 3 cards, okay, card 1, card 2, and card 3, we'll just call them for now, of the same suit. So if I think about those probabilities, then I have 13 out of 52 cards because there's 13 cards in a suit and there's 52 cards in the deck. I'm not putting it back, so this one's, and I want the same suit, so this one's going to be 12 out of 52. Then I'm sorry, 12 out of 51. Then I'm not putting that one back, so that one's going to be, the next one's going to be 11 out of 50. So I took a card out, took a card out. Now, here's the thing about this question. This is assuming that there's only one suit in the deck, okay? But there's actually 4 different suits in the deck. And because the suit wasn't named specifically, it just says same suit. This is not specific. I need to multiply by 4 total suits. I need to multiply this probability by 4 because there's 4 different ways this could happen. This could happen with spades, this could happen with hearts, this could happen with diamonds, and this could happen with clubs. So I need to take this probability and I need to multiply it by 4. When I do that, I end up with 1,716 over 132,600, which we've talked about before. But then I need to take that and multiply that top number by that 4. That's the 13 times 12 times 11. If I multiply that by 4, I end up with 6,864 out of 132,600. And then I can find my approximate decimal, which is 0.052. So a very small probability here. You know, only 5% chance that that will happen, but there you go. So multiplying by 4 gives me one option for each of the 4 total suits, really is what happened there. And then the last one, number 10, it says a cage contains 3 white and 6 brown hamsters. Maggie randomly selects one, puts it back, and then randomly selects another. What's the probability that both selections are white? Okay, so here we're looking for 2 different hamsters that she's pulling out of this cage. Selects one, puts it back, selects another. So hamster number 1, hamster number 2. And the fact that she puts them back means that it's independent because she hasn't changed the number in the cage. She took one out for a brief second, but then she put it back in. So the number in the cage is still the same. So I need to know the total. 9 total, because there's 3 white and 6 brown. And then I need to set up each probability. I want both of these things to be white hamsters, so that's what I'm going to look for. So 3 out of 9 would be my successes here. And then she puts that one back and picks another one out of the cage, so it's still 3 out of 9. Okay, so 3 out of 9 and 3 out of 9. Probabilities didn't change, or the total number of outcomes didn't change because they're independent. 3 times 3 is 9, and 9 times 9 is 81. And this ends up being 1 out of 9. And 1 out of 9 is the same thing as 0.111. And that's actually 0.1 repeating, so I should say that because I'm going to round it. So that is her chances of pulling out 2 white hamsters. Okay, that's going to take us to the end of our notes video. Thanks for listening today, and I will see you tomorrow.